Okay guys, we're now starting our final session. So we've got just 3 more presentations standing between you and the evening drinks social. Now, for some time, distributed ledger technologies and blockchain have been revolutionizing finance and banking. And now, blockchain technology has been touted as a solution for the construction industry. Here to explain more is Dr. Eleni Papadonal. I still can't do it. Dr. Eleni P.
Good afternoon, everyone. Thank you for the introduction, and I'm delighted to be here. I've enjoyed all the presentations throughout the day. So my presentation today will be about blockchain, also the next one by my colleague. And the intention is to understand the possibilities out of this technology and how they could change construction industry. So just before I start, a couple of things about me. So I was trained and I worked as an architect for a few years in Greece, in the Middle East, and various other countries. And then I decided I wanted more training, so I was very much drawn to digital architecture and parametric design. So then I studied at Nxtbld, and after that I realized that I preferred management over design. So I went to the management side. And I did my PhD on design and construction management, and I was looking at how supply chains are working with technologies like BIM and digitization. And at the moment, I'm a lecturer at UCL in the Bartlett School of Construction and Project Management, where I'm focusing my research again on BIM and digital, but at the same time, I'm part of the Construction Blockchain Consortium that this presentation will be mostly about. So just an overview of what we will be discussing the next 20 minutes. My point of view starts from the supply chain, so I was always interested to see how different firms work in projects and how all this complexity comes into delivering successful construction projects. And of course, we have all these new innovative technologies, digital, and so on, and they are affecting how we're doing things, the business as usual. So to this end, and all this complexity at the supply chain level, and all this BIM and digital novelties that we are working daily, I will add another complexity in the equation, so I will be talking about blockchain and what it can do for construction. So typically when I speak about construction and BIM and so on, I like this image very much because it's very messy. And most of the times we ignore and we forget how things take place on the site. So this is not a typical site, but still we are familiar with this image, which means that it might also take place. So then when you have this in your mind, and you're thinking about innovation, is this fit for purpose? Can we be innovative and also maintain this culture? So my presentation will be both about culture and structure and how the supply chain works with digital technologies. So in terms of structure, we all know it's a very project-based industry, so we move from project to project. Typically, we don't learn out of this process. And it's an industry which has a lot of high demand, but also supply variability. So many different actors coming together to construct an asset. And typically, yeah, all of us know that it's beyond schedule and beyond budget. So a couple of things of my background. As I said, I studied in the Netherlands. So over there, for those who are not familiar, the construction industry there is more collaborative. So they engage in long-term relations. They work well with one another. They also learn. So I worked and I studied there for 6 years in total. And I interviewed many people. I researched many projects where they were using BIM and how they were using the technologies and taking advantage of the interoperability and capabilities to work collaborative in that. But at the same time, I did observe some I did observe mistrust and fragmentation of information and also lack of risk sharing. So these are problems that even in the most collaborative industry, we can get them. And then naturally, when I moved less than 2 years ago from Holland here in London, I saw these problems even more emphasized in a sense because it's a larger industry, way more fragmented, and this collaborative culture, I understand it's not really there. So apart from these structural characteristics, of course, we know that it's very fragmented. So we have many small companies, SMEs, working around and trying to deliver projects. And we have many different tiers, and it's more hierarchical than network. So we have a contractor and so many different subcontractors who are delivering things, and they are unknown one to the other what the firm next to them are delivering. So typically in construction, we have many different tiers being engaged in all this process. And yeah, the structure, as I said, was more central. So we have a contractor who holds all the contracts, like the spider in the web, as they say. And then, of course, this has implications for culture and how people interact. So typically, construction has a very adversarial culture. People have a very blame culture. They blame one another. They don't trust. They don't share information. And trust also is of many different types. So it's not only interpersonal trust. It's also trust about how well they could do their job, how trustworthy and reliable is their data and the information that they're sharing, and at the same time, whether they want to help, the goodwill trust, as we say. So all of these problems, trust, they're still there. We have new technologies, but they're still there. And this is what we'll connect later on to our discussion about blockchain. Blockchain is an innovation. So before discussing about BIM, blockchain, and so on, a couple of things about innovation. Typically in construction, when we talk about innovation, we always import it from other sectors. We might develop stuff, but most of them are innovations in manufacturing or other sectors that are, in a sense, important in construction and adjusted for our benefit. And of course, even when they are important, they're very slow to adopt. So typically, people in companies, they struggle to change and to adopt them. And of course, there are differences across tiers and low digitization everywhere. This was one of the projects that I enjoyed more when I was working more than 10 years ago. So all of you must know the Burs Tower there. And it was one of the projects that people essentially say that was one of the first BIM projects where BIM was used. My experience as an intern there was that essentially all these panels, everything was designed AutoCAD. So from the moment it went to the subcontractors, from the moment the design was awarded, everything was 2D and everything was designed by hand. So we had to design 3,000 different GRC, glass reinforced building components to clad the whole complex. So we're talking about innovations, but still we're doing things very traditionally. This traditional mentality, people are feeling that they're pressured by time, that they're approaching projects just from the money perspective. They don't trust, they don't show all the cards on the table. But at the same time, because of all the digital, we have been hearing people coming together in the table to discuss more and to move towards a more digital delivery, and at the same time, rejecting the old ways of doing stuff. So that's a very positive sign, but at the same time, you are all familiar, I would assume, with this graphic from McKinsey. At the same time, construction is here, right? So at the very bottom of this matrix. So typically, it's not digitized, and their criteria here, I don't know how they did the analysis, but they have assets, so we do know our assets are not digitized. The use of information, the same, so all the transactions are completely analog in a sense. or at least not fully digital, and of course labor, so work. All these are done in a traditional way, and many other industries are doing much better than us. And a couple of things about BIM. So I like the word modeling inside the building information modeling word. And actually I like it because it's not only 3D modeling. What most people have a reaction to is to use interchangeably BIM and 3D. It's not the same, of course, because modeling in a structured way of information can help you essentially maintain some level of consistency and structure in how you're setting your information. So I'm agnostic as to software and so on, as long as we can use some models and data models that can help us support our work. And at the same time, we of course have a 3D model, but a modeling database in a sense. So we have different information about objects, either material, energy, cost, and so on, that we can use to manage the process. You've seen this image? So if you go Google BIM, you will get something like that, right? So BIM is in the center. Everyone around is very happy. They're very much supported in their work. But this is, I'm allergic to this image. This is not the reality, actually. This is very far from reality because we essentially have many different teams, either in the office or in construction or in the client, where they're working using different means. So we have a hybrid way of working in projects. We have, yes, the digital, yes, the electronic emails, a lot of phone calls, a lot of meetings, a lot of co-locations. So there are many different means that we daily use to do our work. So BIM is essentially not a quick fix for all this complexity. And indeed, there are some persistent challenges in a sense. Accessibility, IP, people in firms, they talk a lot about not wanting to share their commercial advantage, accountability, provenance, who did what, to what extent is this information right. And of course, other challenges are more technical, like interoperability. Yes, we're doing steps towards that direction, but still the real-time, fully interoperable BIM and so on, they're not there yet. So we still have many steps. And at the same time, although we have benefits undoubtedly, we still cannot change this whole transactional mentality of construction by simply using BIM and simply using a technology. So we cannot increase the trust. Here is where it goes to the blockchain part of my presentation, essentially. And I use this introduction, rather long introduction, to show you where I'm coming from and my perspectives from the supply chain and BIM side to the blockchain. So that's a persistent problem. That's at least my own problem or my worldview. That's what I'm interested in, the supply chain relations and how they are very tense and how they're so unstructured and so complicated. And they're not helping towards a successful delivery of projects. At the same time, you have all this discussion about digital and BIM. And the next step is to discuss how blockchain could help the future. So blockchain. Anyone here is familiar with blockchain? Yes? Yes? Would you like to? No. That was easy. OK. So I will provide some background. And of course, everything is open for discussion. So most of you have seen these diagrams from Bitcoin. So my title of the presentation was also that we're looking beyond cryptocurrencies. So it won't be a presentation about cryptocurrencies of Bitcoin and so on. So sorry for those of you who wanted to see that. So I will focus more on the blockchain. And this is a very basic diagram of how the Bitcoin blockchain is organized. So essentially, there are some packages like that, which are called blocks. And each one has a tree there, a hierarchy there, which has other transactions in some specific size, length blocks. So this is useful in order to understand. This is useful in order to understand the key concepts of the technology. So essentially, distributed ledger technology is a cryptographically assured and synchronized record of consensus. Consensus is very important as a word because essentially this is what we're looking for mostly in construction. That's the uncertainty that we have, and we don't trust people. So it's good to find a technology which can support that. And at the same time, there are different ways to implement it, essentially, different ways to design this ledger. And it could be either centralized or decentralized, depending on the governance and the chosen political decisions to design it. For example, for those who know about Ethereum is decentralized, whereas Corda is centralized. So there are different levels of information and transparency there. At the same time, blockchain technology is an implementation layer of a distributed ledger. So it's something which is helping, essentially, create this blockchain of distributed ledgers, as I presented in the figure before. So essentially, it creates some blocks, some very small pieces of data, which are housed in specific lengths in order to fit some specific criteria, in order to validate and fit some specific criteria. And the way it works is that at the beginning, we have a transaction, that we formulate a transaction. For example, I want to pay this subcontractor, for example. And then we put a request in the network because it's distributed, as I said before. So we're saying, I want to pay this subcontractor. Could you confirm this? And then the network validates the transaction. So the transaction becomes a block, similar to the diagram I saw it in the previous page. And then this block is chained to a public blockchain of other similar blocks and transactions, which could be related to that project, to other projects, to the whole construction industry. It depends on how you design that. And at the end, this transaction is confirmed, and then the knowledge of this, of paying this subcontractor is public knowledge. So you don't have uncertainty, and you can trust people. This is the most visual my presentation can get. So I have a GIF here. This is not, this is a side chain. It's not very helpful to understand the whole blockchain, but it's just to show that they have here a subset, a side chain, so, and some computers linked who are preparing some packages of information. And then all this information, all these blocks which are created, they're added to the public blockchain. So this is how typically it works. We have a network validating and then becoming, through the block, part of public blockchain. OK, and we have seen many different applications in other sectors. So for the rest 5 minutes, I will be discussing what we can do with this, with blockchain and what we have. So we have seen a lot of applications, of course, in finance, typically more for utility and commodification. So we have all these coins and the cryptocurrencies and the tokens and so on. So this is one application that could be one application of construction. At the same time, we could have more transactional focus and use this blockchain way of doing things for payments, micropayments, and using more transparency in how we are implementing our contracts, essentially. In logistics, there are many examples from other sectors, from other examples like agriculture, industry, food, logistics, and so on. So what they're doing there, they're essentially using blockchain in order to provide transparency for business-to-business systems and create information which is, it has quality. They could use it for quality assurance, assurance for insurance of these shipments and these different transactions that are part of their logistics approach, but at the same time for transferring ownership between packages and assets. In healthcare, there are many blockchain applications in healthcare as well. So typically they're used for data integrity and management, mostly IOTA, and also security and privacy. So most of the people think that if we have blockchain, it's public and so on, so everyone knows my data. That's not right. That's not how it really works. Security can be essentially provided by blockchain. So from all these, before I got to that, so from all these, we can pick and choose essentially what we want. What do we need in construction? Trust, transparency. So we can pick and choose from the applications because, as I mentioned before, typically construction is one who imports innovations. So we have some examples that we can use to work towards blockchain in construction. And as I said before, it has to do with we could have centralized, decentralized ways of using some blockchains, but where we want to go typically is at a distributed level so that everyone can be part of a network. So because construction is, at the moment, when we are in projects, is very centralized. So we have contractors who are holding all the cards and so on. And we want to move towards a more horizontal approach of managing projects. And at the same time, a part of changing the structure of construction, there's an argument for changing the culture. So blockchain in construction will help people, support people in understanding this argument about the digital. Because if we don't understand and do something now, there will be a blockchain imported to construction from a top-down level. So we won't have time to design to our needs. We typically, will typically increase trust among different parties in firms, teams, and among people, because blockchain will help how they are understanding and how they're using information. And at the same time, we can ensure data integrity and provenance, essentially accountability. Some of the applications include smart contracts. Smart contracts could be used for many different applications, like insurance claims, Internet of Things, keeping records, just basic stuff, transactions, payments, and custodianship of information. And of course, it is code. Typically, they're written in Solidity. That's a very popular language. So this is a payment essentially using a coin. So that could be also application for construction. Again, this is payment of employees, of people, and this is an example of selling and buying energy quota, essentially, and crediting. So typically, a blockchain, as I said, is the underlying implementation layer of a distributed ledger. So a distributed ledger means that it is in a public domain, in a public blockchain ledger. However, this is how we're doing things at the moment, at least in the financial sector. So we have a very big bank and so on. However, there is also opportunities for private blockchain ledgers. So this is also a decision making, and a debate always to decide what's the best fit for construction. Are we going to go for a totally public blockchain or a semi-public private blockchain, or are there going to be many blockchains or a huge one with some side chains and so on? So all these are issues to further develop. So what we are doing, the CBC, the construction blockchain consortium, we are essentially an industry-academia collaboration. So we started 2 years ago. Thank you, Abel. We started 2 years ago. The mission essentially is not only to increase all this awareness and share knowledge about blockchain in construction, what's coming actually, but also to do research and development. So the past years we have, we are non-profit, but we have gained funds and we have coordinators now, and we will start doing more research and design, and of course education and training. So we have several strategic partners, and it's nice to see that we have essentially competitors also. So we like that we have competitors coming together at the same table to discuss how to create solutions to increase trust and transparency in construction. And at the same time, the CBC is member of different semi-public blockchains, like the IBM Hyperledger, and we are also supporting knowledge exchange with the Accord project. Yeah, a couple of conclusions, just to leave them there. The construction supply chain, at least for me, that's my motivation, that's my starting point. We have a lot of digital, a lot of technology, but it's not promising to make things more easy. It's essentially adding to the complexity. So one of the solutions is to try to change both the structure and the culture of construction using blockchain. Thank you very much.
Thanks, Mark. Cancel. Good job, Shane. All right. So, after conducting substantial research into BIM, including ways to overcome some of the scalability challenges that teams face, our penultimate presenter is here with some tips for preserving not only your design intelligence, but also your design intellectual property. Please welcome to the stage Dr. Abel Marcial.
Working. Thank you very much for inviting me. It's an honor to be here. A little bit about myself. I'm a senior research fellow at the University College at the Architecture School of Bartlett School of Architecture. I've been working for quite a few years in the industry as an architect, and then eventually I did an engineering doctorate in virtual environments, and I'm the founding director of Design Computation Limited. And I have a group called designcomputation.org, and we have a wiki on computational design, and it's something that is free and accessible for everyone. And I'm one of the founding directors of the Construction Blockchain Consortium with Professor Alan Penn and Professor Philip Treleaven. And we just heard from our colleague, Eleni Papadonikolaki. And my main interests are really design and choice, and how we decide between different options in design. And in order to understand this better, I've been looking at lots of different emergent technologies like AI and machine learning, human-computer interaction, computer-supported collaborative work, BIM and BIM, behavior modeling and game theory, ethnographic methods, and distributed ledger technologies. So at UCL, we have a number of grand challenges. They are related to justice and equality, human well-being, cultural understanding, sustainability, and cities, and global health, and transformative technologies. So UCL as a whole is looking a lot into food security, inclusive growth, future of work. That's a very big topic with machine learning, climate change, finance, the internet, and what the internet will become with new technologies, global trade and investment, and long-term investing, and with the fact that we are living longer, and healthcare in the future. Two things that are very relevant for us is like sustainable cities, of course, and the transformative technologies. So I'll talk a little bit about the work I've done on build information modeling and how I've been using build information modeling on my consultancy on design computation. So I was very privileged to work on some very challenging but very interesting projects, like the Apple campus in California, the Google campus in California, the Google campus also here in King's Cross, a very complex, geometrically complex project, The Vessel by Thomas Heatherwick, a very interesting project, and also the Royal Theatre of Rabat. We heard a little bit about the theatre this morning. Used to collaborate with the engineers on that. And what is very interesting about BIM, in my opinion, is that BIM, as it is presented today, is it's a kind of a visual object-oriented programming. It's very data-rich, and in BIM we have things like placing objects, embedding, open and close objects, in place and adaptive modeling. And akin to this, we also have in object-oriented programming things like abstraction, inheritance, encapsulation, and polymorphism. And but this is not so intuitive for the designer. It's a very different way to design and compose your build information model. But it is a kind of parametric object orientation, and you place objects into a project environment, and you compose a piece of architecture, a building, and eventually use this information to do facilities management and to recycle the building. With the development of BIM, we start to do things like simulations and reporting, like energy simulations. This is the canopy of the first phase of the Google campus in Mountain View. So the first phase is called Charleston East. And with the simulation and reporting, we get this ad hoc feedback on the different options, and this guides us through the decision-making process. So we came up with lots of different strategies to place solar cells on the different modules of the canopy. And it was in a kind of assisted decision-making process by the software. Akin to this, we have also the collaborative tools that we see emerging in different BIM platforms. So on this particular project that I helped, they spoke of a master plan just outside Moscow, and it was something that I worked with Valodin Piste in Paris and the Arup team here in London. And was a very large team, collocated. Everybody was working on the same floor at Arup here in London. And we could very quickly visualize who was doing what and what sort of work set they were working on, what they were changing on that work set. And by using the build information model, we could set up very quick meetings to clarify what was going on. And on this particular project, we had the architecture team together, sitting side by side with the engineering team, and it was incredibly productive. So going back to the Google campus, one thing that we realized was problematic was the gradual handover of the design architect model to the delivery architect. The delivery architect for this first phase of Google was Adamson in California, and we had to develop this kind of a ghosting method where they would have access to our build information model and gradually rebuild everything, although we were pretty sure about what we were doing. And we all thought this was incredibly wasteful. And I started to think if there are better ways to do that. This slide really breaks down on a longer presentation in many slides showing how this ghosting method was deployed. But basically, because the build information model was very complex, they decided to rebuild it so they could understand exactly what was going on. And I think there is a huge inefficiency in that. Yeah. Something else about build information model is the interoperability strategy that we have to think about. Of course, this is gradually disappearing. We are connecting data in much better ways, but there is an obstacle there. And when we start to look at the interoperability and this object-oriented way of modeling, we can start to see that blockchain would be a technology that would be very helpful. And with the implementation of blockchain in build information modeling, we also come up with opportunities to better protect our intellectual property. So I think at the moment, I think most people here would agree that build information modeling is very front-loaded. Architects and engineers, they have to work extremely hard to compose a reasonable build information model. But eventually, we create this parametric knowledge legacy for the project. And there is an increase of knowledge and intellectual property that we need to protect. So we'll talk a little bit about emerging disruptive technologies. I'll be very brief. But I think nowadays, and especially today, we've been talking about a number of interoperability challenges. Things like cloud computing, concept simulation, computer-supported collaborative work and design, assisted decision-making, big data, metadata, or data in general, programmatic design, things like generative design and scripting design in different forms so you achieve high efficiencies on managing change, reality capture, virtualization, and building management systems. These are, I think, I might be missing something, but I think these are the main things that we have to improve in terms of interoperability and linking data and making data more transparent across all those different applications. And the emerging technologies are things like the Internet of Things, as a cover term, artificial intelligence, including neural nets and machine learning and deep learning, etc. Distributed ledger technologies, virtual environments, computer-supported collaborative work in general, human-computer interaction in user experience, and automation in general, like digital technologies and so on. Like blockchain is something that we can generally classify as under a distributed ledger technology. And there are lots of synergies between them. So when you improve a feature or come up with some new technology for one of those categories, they will affect how the other technologies are used. So that we kind of has to, one would have to cross-map the interoperability challenges with the emerging technologies. Then I'll focus a little bit on the blockchain technology. So as my colleague said previously, we have centralized databases, decentralized, and distributed databases. On distributed databases, you can set up something called a Byzantine fault tolerance. And this is simply creating public and private keys so you can hold to some data and be able to modify that data. And you can give a public key to somebody else to just observe or have access to that data, but not necessarily change the data. And this is in the field of cryptography. So 3 very key characteristics of blockchain are it's resilient distributed ledger. So by resilient, I mean it's not to say that a centralized database is not secure, but if the person who controls that centralized database decides to switch the database off, nobody else can do anything about it. So you won't have access to that database. You will have access maybe to a copy of the database somewhere, but it's not as that you can carry on working. Let's say if you have a common data environment and that common data environment is switched off, what can you do about it? The other thing, this wouldn't happen on a distributed ledger database. So immutability is the fact that once you create a block, what is resisted or what that block is pointing to cannot be changed. So in essence, what you're doing is giving physical properties of the real world to digital assets. So for example, if I have a picture and I blockchain that picture and give that picture to you, I will no longer have access to that picture. Yeah? It can be designed in that way. And you can also guarantee provenance. You can guarantee that that data came from that person and nobody can tamper with the data. So with this, you have, to make blockchains, different blockchains work, you have like a few different things going on. So you have, normally if it's a tokenized economy or if it's a tokenized blockchain, you'll have a mining process. You will have to have a proof of work, which is normally a small puzzle to avoid cyber attacks. And this puzzle has to be computationally costly, so people don't simply go there and keep doing funny things to the blockchain with no consequence. And often you also have a proof of stake. In early blockchains, you don't really have a proof of stake, but or you do have a proof of stake, but it's not so robust. The newer blockchains, they are investing quite a lot on making the proof of stake more sophisticated. So, for example, if you using Bitcoin, Bitcoin is mainly a unit of value, and there is a work. You have to mine for that value and create the block. And then there is this proof of work is solving the block. And then if you solve a block, then you get a payment from the blockchain. I think you get, nowadays you get, I think, 7 Bitcoins or something like that, or maybe more, 17 Bitcoin. So over time, the payment that the system gives back to you, the creation of new Bitcoins will decrease. And eventually, I think in 2075, all Bitcoins will be generated, and your proof of work will be, the payment for your proof of work when you're mining for blocks will have to be paid by the person creating the transaction in the Bitcoin blockchain. And some implications are, the application of blockchain have some implications. They are cultural changes. You know, things will operate in a very different way. Some say that a blockchain will be the new internet. And you can create things like very sophisticated smart contracts. And you could have a much better control over supply chains. And you can have something called distributed autonomous organization. So you could create an intelligent agent that will be executing payments, mining, and also creating blocks, and so forth. And that's a very complex topic, and maybe we could talk in detail on our drinks later on. On different blockchains, like Ethereum, you have, it operates slightly different. You have something like Ether, which is a unit of value, and you have gas. Gas is a unit for work. And when you're creating your transaction in Ethereum blockchain, you can decide how quickly you want work to be done, and then you would pay for that work to be done quicker or slower. And then you also have your exchange of value. And by doing that, you have a distributed application running on the internet. And you can create smart contracts using a very domain-specific language called Solidity. Solidity at the moment, I didn't use it very much, but at the moment seems to be fairly simple, and it's just starting to become something more sophisticated. So, well, I can talk more about blockchain later on, because it is a very big topic. And I'll talk a little bit about the research I've done with teams and collaborative design. So I've done a number of experiments at University College, including ethnographies, going around offices in London and observing people, interviewing them, and so on. But also controlled experiments on a controlled lab using software and hardware I've developed myself. In one of the control experiments, some of the data I collected include sketches to change a scenario. So it was a digitalized planning exercise where two architects would sketch a solution, and we had the control session and the experimental session. On the experimental session, halfway through the design process, we changed the scenario. We include some piece of extra information. And by doing that, we changed their behavior. And what this interface and the software was doing was basically capturing everything they do. So was counting the number of vector space catch, seeing how long they were taking to create a sketch, and time-stamping all this. And my hypothesis for this particular experiment was a falsifiable question. Basically, I want to know if by adding the extra constraint when they were designing, when they already had formulated a solution for that design constraint, if they were to increase or decrease critical production, if they would have to come up with more ideas, or if they would just leave it or make minor modifications because of the time pressure. And there was a very strong correlation between adding the extra constraint and increasing critical production. So we got a very high significance, a p-value of 0.008. And this is very, very significant. And although this was a very simple experiment, it shows that by giving information at the right time to the team, they can actually come up with something better. I had other two hypotheses, but they were not as significant as this one. And then I start to look at different ways to model design interaction. And there are many models out there. So you have the classic Gabriela Goldschmidt from the 1990s, linkography. And basically she's trying to capture the ecosystem of good ideas and how good ideas come back to the design as you play the design process. And John Giro implemented a lot on this original idea. And it's really fascinating. The work he came up with is really seminal. It's remarkable. And then we have more prescriptive models like Thomas Ekman and Gray and Hughes. And then all those models, they are either prescriptive or descriptive. They are either looking to improve the design process by prescribing a method, or they are observing what we do. What I've been interested in is how you can actually design the interaction. So to create interactive models, you need to look at human systems, and you need to look at, in particular, the teams. And there is a difference between virtual teams, and collocated teams. I've been looking recently more into collocated teams, people in the same room designing together and using digital tools. And if you come up with a good interactive model of the design process, then you can transform that model into a predictive model. So for that, to model the interaction, you need to play with game theory. Game theory is a type of economical modeling that looks at the behavior between two or more agents. If you want to look into how one person makes decisions, how you decide what clothes you're going to wear in the morning or what you're going to have for breakfast, then you look into things like behavior economics or risk and prospect theory. Game theory is more for multi-agent modeling. In game theory, we have quite a few different things. It's a complex area of economics, and I'll try to make it really brief. So for game theory models or interaction models, you need a utility function, you need a best payoff, you need some sort of motivation, you need some sort of equilibrium, what makes you make that choice given the utility you have. And when you have that, you have a dominated strategy, and therefore you can predict, you have a backwards induction. The predictive formulation of game theory is called economical mechanism design. So I'll see if, so here we have a classic coordination game. So you have a player 1, player 2. Player 1 can go up or down, player 2 can go left or right. And then you have utility. So if player 1 goes up and player 2 goes left, each one gets 1 point. But you have like a dominated strategy here. So for whatever reason, when you create this coordination game, if player 1 goes down and player 2 goes left, player 1 will get 2 points, player 2 will get 1 point. And therefore, the dominant strategy for player 1 is to go down. And the dominated strategy for player 2 is to go left. Yeah? And this becomes more complex. Yeah? So von Neumann was the mathematician who came up with game theory. And John Nash, very famous John Nash, came up with the Nash equilibrium, which is widely applicable in game theory and in many other economical models. And he won the Nobel Prize for that. It's a really brilliant, incredibly simple but brilliant idea. So in game theory, you also have different levels of complexity. They can start very simple, like a complete information models, when everybody knows what everybody else playing the game should be doing. And then you have, and then there are static games. For example, you make a choice, the other person you are working with or collaborating with also makes a choice, and then the game is over. So it's a one-off game, it's just one decision. And then they can become dynamic, so we have many steps. And then they can be of complete information or incomplete information. And eventually, when situations are very large and complex, they become imperfect information. So in game theory or in behavior modeling in general, you have this distinction between perfect and imperfect information and complete and incomplete information. And this has to do with knowing the rules or not knowing the rules, and knowing that everybody knows about what needs to be done, and not knowing if other players know what they should do. Okay, so I need to speed up a little bit. So, and then I came up with a model based on a very known model in economics called the Nxtbld game. It's a simplified version of the prisoner's dilemma. And I modified this game to try to understand how value is articulated in design teams. I can explain this in more detail in some other occasion or outside. And by collecting user stories, particularly from the Google project, and how they were using Beam 360 and Revit and so on, I tried to look at the metadata and spot how collaborators were exchanging information and how I can apply this game theoretical modeling to their decision-making process. And then now, with the advent of the construction blockchain consortium, I'm trying to use a similar process to blockchain the decision-making process, and therefore come up with a more efficient way to protect how people do things, what they are doing, and how this can benefit later projects. So keeping the data that you generate, your parametric knowledge alive and usable for later projects. Something that I've been working recently is on a machine learning method, a convolutional neural net, to automatically understand what an object is within Revit and how this can be used to know what people have been doing and where that family is coming from. So that's very early days. And it's working really well. So the confusion matrix is becoming very clear. So very quickly you can identify what an object is by, and you can use dumb geometry. You don't need to use, say, a Revit or ArchiCAD object. You can wipe all the metadata. You can make the geometry like a DXF or whatever you want it to be. And by just looking to the vectors, you can find out what object it is by the geometrical configuration. And the future research will be really into investigating more what we can do with the Internet of Things and how we control this with some more lightweight blockchain technologies such as IOTA, machine learning, and how by using blockchain we can make the data more machine readable and therefore easier to learn what's going on or see patterns on that blockchain and how this integrates with BIM. So I'm looking at things like IFC, Ethereum, Steam, Neo, and Bitcoin as well, but Bitcoin seems to be more interesting for only value exchange, not so much the execution of work. It's more for the value exchange, the occasional value exchange. And this is my presentation. If you have any questions, let me know. Thank you very much.
Okay, we're going to have a very short hiatus again while we swap over the computers for our final presentation. The advertised program here. Unfortunately, Gregory Epps was unable to join us this afternoon. Thankfully, Daniel Schmitter here has stepped up with a talk about 3D CAD and moving from biomedicine to AEC. So for the next 10 minutes, keeping you from your drinks, but hopefully inspiring you into much more discussion during the drinks. Daniel Schmitter.
Thank you. Is my mic working? Yes. Perfect. All right, so this will be a very short presentation. I just talked for about 10 minutes. First, I quickly want to thank the organizers, of course, especially Martin and Denise and everybody who made this event possible, also the sponsors. Thank you very much for having us. So we are Miracoy, and we're a small startup company from Switzerland. Just have to make sure my laptop doesn't fall down here. All right, don't breathe. So we're a small startup company from Switzerland, and we provide CAD software to do intuitive, fast, and precise 3D CAD. And I want to talk a little bit about the journey that took us to us providing 3D CAD software, because we have a signal processing background. We're a spin-off from EPFL, from the Swiss Federal Institute of Technology in Lausanne. And we were actually at the beginning working on biomedical shape characterization and just modeling for biologists and clinicians and people doing clinical research. So this is a video I'm going to start in 1 second. Just quickly to give some context, the green structure is a very noisy brain outline that stems from 3D MRI data. So a patient goes to the scanner, acquires a 3D scan of his head or her head, and then the clinician wants to extract the brain in order to do some analysis of, for example, Alzheimer's disease or neurodegenerative diseases and so on. And so the clinicians came to us as researchers. This is really early days of my PhD research 5-6 years ago, and told us about this problem, and they wanted to characterize this brain structure. So as you can see, the green structure is very, very noisy with a lot of artifacts, and they want a very smooth and precise model of the brain. So we came up with an algorithm that actually allows the clinician to segment this data pretty fast. So this is 4 times accelerated. So he can do that, or she can do that in a doctor-patient encounter within 5 minutes. And actually the requirement is also that once this brain structure is segmented, the clinicians still want to go and tweak and adjust a little bit the model to increase the precision. Everything should be super smooth. And in the end, you get something like this. So this is really just a brain outline without any skull or bone or none of that. So here's another example of, again, a 3D MRI image. This is the aorta. So this is the heart region. And again, the clinician, they want to outline or segment this structure, and then they want to be able to tweak a little bit the models to increase the precision. So, sorry, I just have to remove the underlying laptop, otherwise my laptop will fall down. Sorry. All right. So this was the early days of our research, and then actually 3 or 4 years ago, there were some folks in the AEC industry that told us, I mean, they saw what we were doing, and one of the requirements for the clinicians was it should be very, very intuitive. So no clinician is ever going to use Rhino or SolidWorks or any of that because it's just too complicated. Clinicians really want something that's fast, no learning curve, and just apply it and it works. And so some folks from the AEC industry approached us and they told us too, we also want that. We also like things that are simple to use, things that are very intuitive and deliver precision. So that's how we started to work on the technology transfer to bring that framework into the AEC industry. Our framework already back then was called Xyrus, so this was the internal research name. And now we brought the geometric Xyrus kernel to the AEC industry. And here I just want to present you a couple of features that we have for the people doing 3D CAD in the AEC industry. So this is all about smooth, organic, free-form shape modeling. So some characteristics, it's direct smoothness control that we offer. I will show in a second what this means. Decoupled access to the surface, tangents, curvatures, tangent planes, higher order derivatives, watertight junctions with G0, G1, or G2 smoothness control, subdivision, it's NURBS compatible, and so on. So I just present you a bunch of quick videos so you see what this is about. So first thing, direct surface control. So this is software that we make compatible for Rhino. As you can see here, this is actually just a plane that you manipulate, and maybe for the people who know Rhino or know NURBS, you can see that this is pretty unusual because you can directly touch the surface when you deform it. When you deform it, it deforms very smoothly. Now for the people who don't know 3D CAD, you would believe, well, this is how it should be done. You know, it's just, you just touch the surface. There's no parameters in the air, no control points, no weights you have to adjust. So this is basically what the clinicians asked us to do. So we worked on the theory and did it. And then we brought it to the Rhino world. Another example is decoupled smoothness control. So we actually allow to manipulate tangents, curvatures, tangent planes, higher order derivatives. And we call it decoupled smoothness control because you can manipulate these quantities independently from each other, which means that, for example, here you can see at each control point location you can display the tangent. You can move the tangent. This is very, very simple. But the control point itself on the surface doesn't change the position. So you're just moving the tangent and not the control point. The same thing you can do with curvatures or tangent planes, and you can really adjust these quantities in a decoupled manner. So if you spend some time to adjust some curvature value, this will stay there. Then you can spend some time to adjust the tangent value. You can spend some other time to adjust the surface point. Everything's decoupled. So this gives you actually some kind of new freedom to operate, or freedom of operation when you do 3D CAD. This actually gives you new ways of doing surfacing or come up with surface shapes that you cannot do if you just have this very classical NURBS-based control point structure. Maybe just I switch forward the video to show you something about tangent planes as well here. Sorry, just very quickly. because I know everybody wants to get the drink. Okay, sorry, it doesn't quite work. Well, anyway, I will show you another video in a second. So another thing that people in the AEC industry that work with us, they really jumped on this. We didn't know this is such a big deal or such a huge requirement, but it's to create watertight junctions between surface patches. So what we have come up with is a very simple way of just choosing patches, choosing edges on patches or subsegments, and just connect them, and it's independently of topology. So for example, here you can just connect a box or a square shape to a cylinder that has a circular shape, and you can just choose what kind of continuity you want. So you have, for example, different options. You want G0, G1, or G2, and then you can just, with a bunch of mouse clicks, get some previews, and then you can choose the one you want, and you have it, and this is basically, if you apply an offsetting operation, you can manufacture this surface. So this is really quick, very simple, and just gives you some kind of new opportunities to do some surfacing. In this example, you can create a star point or a star junction. So some of our collaborators really like to manipulate or to adjust the continuity at star points and star junctions. For example, when you do piping or create some complex roofs of buildings, and so on. Then another thing I want to insist on or highlight is this is 100% NURBS compatible. So it means that at any point during your modeling framework, you can change the Xyros structure into a Rhino built-in NURBS structure. And then you can just move on with your NURBS-based modeling workflow, or if you have certain scripts or your modeling pipeline depends on NURBS, you can just apply it. And it also works backwards. So you can also have a NURBS object and just convert it into a Xyros object. And as soon as you do that, you have access to tangents, tangent planes. You can modify the continuity between surface patches and the junctions, and so on. So this is really both ways backwards compatible. Another thing that I want to highlight is that every single NURBS command or BREP command, if you know about the Rhino modeling workflow, is applicable to a Xyros object. So even if we don't specifically provide this operation yet, you can, for example, do trimming, offsetting, filtering, chamfer, all these kind of things. Just apply any NURBS command to this object and it works. Subdivision local refinement. So this is actually subdivision compatible. So we have our own native Xyros subdivision algorithm. So this is especially useful if you do local refinement, if you want to add certain details to the object, to the surface, or to the volume. So you just can introduce a new control point. Again, the new control point keeps all the characteristics of any other control point. So again, you have this access to higher order derivatives, curvature, and so on. So this is, again, really simple and supposed to be intuitive. Then the last point is it's free. So you can just go to our website, you can download it, and it's completely free. This is because at the moment this is still an alpha version, and it's actually quite robust. We work with a lot of people in the architecture industry, jewelry industry, industrial product industry, also furniture design, and so on. And we really try to get as much feedback as we can from these people because it's the users who help us to shape the final product. So we really try to engage in conversations and get the feedback so that we can actually understand what are the needs, because again, we are still signal processing people and we started in biomedical imaging. So if you like what you see, then just go to our website, download it, engage in a discussion with us, send us an email, go to our forum, and just tell us what you would like to see there, what you think is not working, what is missing, and what kind of features you want to have in the final product, and we try to think about it. All right, thank you very much. That's it. Have a nice cocktail.
I'd just like to take this moment to say a few thank yous on behalf of the AEC Magazine and Nxtbld team So first of all, to all of our presenters, I think they've given time to put these presentations together and then to come here and share all of their work with you guys. I think it's very much appreciated. We wouldn't have this conference without them. I think there's a big thank you to the sponsors who obviously give their time and money as well to make this event happen. And then a really big thank you to the whole team here at the Congress Center, working on the technology here and also in the catering, taking care of us all day. I think the food at lunchtime was superb. And so finally, I guess a big thank you to you guys. If you didn't come, there wouldn't be a conference to put on. So that's it. Go and have a drink, enjoy yourself, safe trip home. Thank you.